Hey everyone, today we're jumping into page 40 using properties of inverse trigonometric functions. So we're going to take some of that stuff we did on page 39 and take it a little bit further. It's important to recall that if you think about functions that are inverses of each other, that they both contain x in their domains, then their compositions will give x as a solution, right? If you took two inverses, what that's saying is what we did to prove inverses. If you took f of x and f inverse of x and you composed them. So what that would look like is like f of f inverse of x, and you plugged f of x into f of x, f inverse of x into f of x. They would all cancel out and you would just get x as a solution. With that in mind, it makes this a very easy topic for certain parts of these problems if you know what the properties of your trig functions are. So we got to write those down. So on this left side here, it says if blank, then sine of sine inverse or cosine of cosine inverse or tangent of tangent inverse, right? These ones all have the regular trig on the outside and the inverse trig inside the parentheses. So if something happens, all of those situations will simplify to just x. So let's talk about those. That has to do with what we talked about yesterday with the range of our basic trig functions. So if the range of the trig function lines up, then it's going to work. What that means is, for example, with sine, as long as x is a value between -1 and 1, and it can equal -1 and 1, then it would simplify to just x. Cosine was the same way. Cosine used the same properties, that the range was -1 to 1. So as long as x is between those two values, you will, no matter what, get a solution that just simplifies to x. Tangent's a little bit trickier because we know that tangent had a range from -infinity to infinity. So let me back up there. We can't put a less than or equal sign, right? Because that doesn't work. You can't be equal to infinity or -infinity. So as long as x is between -infinity to infinity, it will give us a solution that just simplifies to x. Now on the right side, this talks more about the domains that we talked about with the inverse functions. The inverse function in this case is on the outside of the composition, and the standard trig is inside. Again, all of these simplify to just x as long as it matches up with the domains we learned yesterday. So the domains we learned were this, that -pi/2 has to be smaller than x, which is smaller than pi/2. Ooh, that came out not great. Pi/2. In other words, this was saying that sine always happened between quadrants 4 and 1. Cosine, we knew it was a little bit different. Instead of doing 4 and 1, we did 1 and 2. So x is between 0 and pi. And last was tangent. And tangent looked very similar to sine, except you couldn't equal the pi/2's. So -pi/2 is less than x, which is less than pi/2 without the equal signs. And again, as long as those things happen, you simplify to just x. What you're going to find with these problems is whenever the inverse is on the inside, it's a lot easier because there's less to stress about. If the inverse is on the inside, excuse me, if the inverse is on the inside, there's less things that can change, that could adjust the problem. And we'll talk about that in a sec. But if you look at example one only focuses on situations where the inverse is on the inside. See how those all have cosine or sine or tangent inverse or arc, sine, arc, cosine, arc, tangent. Remember, those are the same thing. But the inverse is on the inside. So if that's the case, all we're focused on is sine and cosine between -1 and 1? Tangent doesn't matter. As long as they're between -1 and 1, it works. So what we look at here is we say sine. So is it between -1 to +1? And the answer here is -1/3 is yes. That is between -1 and 1. So since it's between -1 and 1, we can apply the rule. The rule says if x is between -1 and 1, sine of sine inverse of x just becomes x. In this case, x is -1/3. So all that's going to happen is the answer is -1/3. That's it. That's all you have to be able to do is check if it fits into the range and then use the property by canceling if it does. So let's look at this next one. We're focused on cosine here. We know cosine is likewise -1 to +1, and we want to ask ourselves, is the number being given between -1 and 1? So our number is 2/5. Is that between -1 and +1? And the answer is, yes, it is. It is between -1 and 1 because it simplifies to 0.4, right? So since it simplifies to that, our answer is just that number, 2/5. The arc cosine and the cosine are able to cancel each other, and the property applies because it's between -1 and 1. All right, number 3 here says we're focusing on 3/2. Again, we're doing a cosine. Cosine is always -1 to 1. Is it between that? In this case, 3/2, that would become 1.5. So no, that number is bigger than 1, meaning our solution does not exist. So if it's outside of the domain of -1 to 1, you have to say it does not exist for sine and cosine. Now tangent, don't get tricked up. Tangent is different. In this case, I'm focused on tangent. Tangent is -infinity to infinity. Is there any number outside of that? No. So because this number is in between -infinity to infinity, you're always going to say yes for tangent. It always works. So tangent, we get -9/2, and that is okay. Tangent can be any number, but sine and cosine has to be restricted from -1 to 1. So with that said, that covers how to do these ones. Very easy, no tricks to this left side. If the inverse is on the inside, it always just is pretty simple. Now, if the standard trig function's on the inside, meaning the inverse is on the outside, it gets a little bit trickier. Example 2 doesn't quite get us there. Example 2 is going to look very much like example 1, except we're not looking at these values. We're going to look at these ones instead. So as long as it's between -π/2 and π/2 for sine and tangent, or between 0 and pi for cosine, it's going to work just like we did before. So taking a look at this first one, it says we're looking at the arc sine of the sine. So again, notice the standard trig is inside, so we're using the π/2 stuff and the 0 to pi stuff. So sine has to be between -π/2 to +π/2. So we got to look here. Our answer is π/4. Is π/4 between -π/2 to π/2? And the answer is yes. π/4 is smaller than π/2. It's 1/4, while π/2 is 1/2. So because it is smaller, we're just going to put π/4 for our solution. The second one here, we got cosine. Cosine, remember, is a little different. It's not the same as sine like in the last one. In this case, cosine focuses on 0 to pi, between 0 and pi. So is 5π/6 between 0 and pi? And again, we're going to say yes. 5π/6 is a little bit smaller than pi. It's getting close to pi, but it's still smaller. So we're going to put 5π/6 as our solution. So the solution, again, continues to just be whatever the number was that is inside those parentheses. Now, tangent doesn't get the same rule as last time. Tangent up above, when the inverse was inside, like in this one, it didn't matter. The number doesn't matter because it's -infinity to infinity. It always works, so it doesn't matter. That rule does not apply here. Tangent has restrictions when regular tangents inside and inverses on the outside. So now we got to focus on that -π/2 to pi/2. So tangent is -π/2 to pi/2, except it's a little bit different. In sine, it's allowed to be equal to pi/2's, but tangent, it's not allowed. So is -π/2 technically inside the range? The answer here would be no, because it cannot equal -π/2 with tangent. Remember, sine does equal, but tangent cannot. So in this case, it would be another example of this answer does not exist because that represents the asymptote of the tangent function. Last one over here, looking at this sine. We know sine is -π/2 to pi/2, and unlike tangent, it's allowed to be those. That doesn't really matter here. Is Negative pi over 3 in between those two numbers. Yes, negative pi over 3 is a little bit bigger than negative pi over 2. So that one is going to work. So we get negative pi over 3 as a solution. So you can see it looks very similar to what we did up above, except instead of using numbers, we use the radians as our solution. So here's where it gets a little bit trickier. If the regular function is on the inside, if it's the regular function on the inside, we can address what other solution would give us that solution. So what I mean by that is we're going to work those out. These ones aren't going to be ones that you could just cancel out the answer. So take a look at example 3. Let's talk about what we mean by that. If I looked at example 3, the first question I would say is it's a sine function, and sine has to be between negative pi over 2 to positive pi over 2. Is this one between those two numbers? And we would have to say no. 3 pi over 4 is definitely bigger than pi over 2. What makes this one a little bit different, though, is you can't just say, oh, it doesn't exist anymore. Instead, we solve it from the inside out. So let's look at what that would look like. We're going to take the arc sine, but we're going to solve the inside. We're going to say, okay, well, we can't just cancel it. We can't use the property cancel, but what does the sine of 3 pi over 4 actually equal? So we know that at 3 pi over 4, thinking about our unit circle again, it's very important to know that. At 3 pi over 4, the coordinate is negative radical 2 over 2 and positive radical 2 over 2. And we know sine is represented by the y-coordinate. So the y-coordinate there is positive square root of 2 over 2. So I can write positive square root of 2 over 2. Now when I go to take the arc cosine is restricted from negative pi over 2 to positive pi over 2. So we have to say, when does sine give us radical 2 over 2 as a solution, but only in quadrants 1 and 4? Well, the only spot that would happen is in quadrant 1, so we would say our solution here is pi over 4. So again, we know that at pi over 4 on the unit circle, we get square root of 2 over 2. And at 3 pi over 4 on the unit circle, we get square root of 2 over 2. They have the exact same answer. But with inverses, we restrict sine to only quadrants 1 and 4, which cuts off the 3 pi over 4. So the only solution that ends up working is the pi over 4 solution. So be mindful as you work through these that you have to think about your restrictions. So if we look at this next one, tangent is always between negative pi over 2 and pi over 2. In this case, again, you can see that that doesn't work. All of these are going to kind of be like that. Tangent's not between negative pi over 2 and pi over 2 because it's pi, so it's bigger than pi over 2. So let's work our way out. We're going to keep tangent inverse on the outside. And the tangent of pi, well, tangent is always y over x. And at pi, the coordinate is negative 1, 0. So we have 0 over negative 1. 0 over negative 1 does just become 0. So when does tangent equal 0 between negative pi over 2 and pi over 2? Well, it's going to be at 0. Kind of weird, but we get 0. So 0 radians or 0 degrees, however you want to think about it. But 0 pi is going to be when tangent equals 0. Maybe we can add that there just to clarify a little bit. Let's put the pi there just so we know that we're talking about the radians. Now, you would not usually put that, but I want you to be aware that we are talking about the radians. At the unit circle, at this spot is when tangent would equal 0. That's what I want you to be aware that you're writing right there. All right, over here, same thing. Sine is between negative pi over 2 to positive pi over 2. Does that happen here? No. No, 11 pi over 6 is way bigger than pi over 2. So we got to, again, work through that solution, see what we can come up with. So in this case, sine inverse, I'm going to solve the inside. So what is the sine at 11 pi over 6? Thinking about our unit circle, we know that at any pi over 6, the y-coordinate is always 1/2. So I know it's going to be 1/2. And since 11 pi over 6 is in quadrant 4, the y-coordinate would be negative, so this is negative 1/2. Again, all that is me using my unit circle very confidently. Make sure you're still practicing that. So now we say, okay, well, when does sine equal negative 1/2? In the inverse restricted. So only quadrants 1 and 4. Well, 11 pi over 6 was in quadrant 4, but we don't use 11 pi over 6. Remember, we use it as negative pi over 6. So I know that this would be negative pi over 6 as my inverse solution. All right, we got one more to do here. We want to find the arc cosine of negative 4 pi over 3. I think you're getting the point here that cosine has to be between 0 and pi. Is this between that? No. No, it is not. So we're going to have to go ahead and solve this from the inside out. So keep the arc cosine. What is the cosine of negative 4 pi over 3? Well, negative 4 pi over 3 is going backwards on the unit circle. So let's think about that and think what that would be. So here's the negative direction. 4 is bigger, so it's going to go to the third section. That looked ugly. So it's really going to be over here. It ends up in quadrant 2. So that spot right there. So for 4 pi over 3, cosine is the x-coordinate. I know that at pi over 3, the x-coordinate is always 1/2, just like we just did. And it's the x-coordinate in quadrant 2, so that's going to be negative, so negative 1/2. And now we can just take the arc cosine of negative 1/2, restricting it from 0 to pi. I know that comes out that it's going to be at 5 pi over 6 then, because it has to be in quadrant 2, so it can be negative. And that would be our solution. That's not right. 5 pi over 6 is not right. We're talking about thirds. Sorry, I did sine in my head. This is going to be at 2 pi over 3. That's it, because it's pi over 3. Sorry, cosine is 1/2 at pi over 3. So we want to do 2 pi over 3, which still would put us in that second quadrant. All right, hopefully this helps you out. Again, unit circle, very important. If you know it, you probably felt a little bit more confident than those that didn't. Keep practicing and you'll get it.